I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. Today, our students of 3rd year Biomedical are going to do a case study on the use of filters in biomedical signal processing. Normally, in signal processing, we prefer digital filters for desired frequency response for our physiological signals. And here we use the technique sampling to convert our analog signal into discrete values, and with the help of quantization we can convert those discrete points into digital values. Normally this digital filters use the technique FIR and IIR to give output like feature extraction, data smoothing and noise removal techniques. Shall we start the case study?
Yes, ma'am.
Start.
So, while talking about the use of filters in biomedical signal processing, so the filters are very essential because in medical fields we record signals like EEG, ECG and EMG. So these signals have some noises, so these are filtered by the filters, and without filtering it is very difficult for the doctors and researchers to interpret the physiological informations. And we have notch filters and high pass filters and low pass filters too.
As you can see, there are 4 types of filters based on frequency response. They are low pass, high pass filter, band pass filter and notch filters. In low pass filters, the low frequency are allowed pass and high frequency components are eliminated there. Like for example, eliminating muscle artifacts in ECG. For high pass filters, it's quite the opposite of low pass filter. It allows high frequency and eliminates low frequency. In band pass filter, it's to a specific range. It only selects a specific frequency range, like isolating brainwave rhythms in EEG. For notch filters, it is a narrow frequency. It selects a narrow frequency, like most probably like 50 or 60 hertz.
Now, what about FIR and IIR filters in digital filter design?
As you can see, for FIR filters, it's finite impulse response. It only depends on a limited number of past inputs only. Stable and they preserve the waveform shape. For infinite impulse response, that is IIR filters, they depend both on past inputs and past outputs. They achieve for a sharper filtering with lower order, and it may not also be stable at sometimes.
So, as Ansini said about the types of filters, I remember a real-time case study where a 54-year-old man was admitted in the hospital for a routine cardiac test. So, they recorded the ECG. It had some power line drips and the baseline drips. So, they used the notch filters, 50 Hz notch filters in IIR filters to remove the baseline drift and the power line interpretation. In FIR filters, they used low pass filters and high pass filters to remove the noise so that the cardiologist can see the PQRS wave properly without the unwanted noises.
So hopping on to the advantages of filters, the main advantage of filters in biomedical signal processing is that they are very significant. They play a significant role in BSP. Firstly, it is used to remove noise. For example, it can remove the interference, line interference and motion artifacts from the produced signal, which makes it more clear. And then it is used to enhance the important features in a given signal. For example, in QRS complex from the ECG signals, and then alpha waves from the EEG signals. And then it can also be used to improve the diagnostic accuracy. It allows doctors and algorithms to focus only on the required part of the medical signal. And filters are also adaptable. You can use low pass filter, high pass filter, band pass, and also adaptive filters depending on the type of signal and the kind of artifacts present in it. And filters are also available digitally in real time. For example, you can use it in wearable devices and also patient monitoring devices where immediate feedback of the signal is required. So these are the advantages of filters.
I think we should also focus on the disadvantages of biomedical signal processing. Filters can cause signal distortion. The original biomedical signals may be removed or altered. While removing noise, there is a risk of losing useful information, especially in ECG and EMG signals. Real-time monitoring filters often reduce time delay in emergency situations. These are the disadvantages of biomedical.
What are the applications of filters in signal processing?
Let's see the applications of filters in biomedical signal processing. Firstly, we can see in ECG signals where noise removal and feature the extraction to detect the arrhythmias. And EEG, it helps to identify the brain rhythms for epilepsy diagnose and sleep studies. In EMG, it uses to separate the muscle activity signals from the body signals, and medical imaging signals are used to enhance for improved clarity and accurate diagnosis.
Okay. I think we will get a clear understanding about the use of filters in signal processing.
The filters are so important in biosignal processing, so it has so many applications. Let's see the applications. In ECG, it uses to remove the noise and feature extract to detect the arrhythmias. In EEG, it helps to identify the brain rhythms for epilepsy diagnosis and sleep studies. In EMG, it uses to separate the muscle activities, signals from background noises. In medical imaging, signals enhancement for improved clarity and accurate diagnosis. Let me conclude with this one point, which is filters act as a backbone of the signal processing.
I think we will get a clear understanding about the use of filters in biomedical signal processing. Normally, we prefer digital filters, either FIR or IIR, based on our application. And these filters are mainly used for noise removal, feature extraction, as well as data smoothing and sharpening our physiological signals. Thank you.
Thank you.